the Crocus Urban IFL, and welcome to the cross-USL IFL seminar of today. We have two speakers today, and the agreement was that the person who the IFLs that are not presenting are the ones who MC the meeting. So here I am introducing the meeting to you. Dave Saylor will then introduce the speaker. So why air quality? Air quality obviously is critically important for our environment. It has incredible connection and strong connection to the climate system as well as the people systems, which is really a key component of the urban integrated FEAR laboratories, particularly the integrated piece. So we have 4 IFLs. As you know, each IFL works on air quality in different ways and in different aspects and with different intensity in scope. But everyone everyone's work is relevant for air quality, whether it's just observations, modeling, or anything else. With that, thank you again, and I will leave it to Dave to make sure that we have enough time for both presentations and a discussion to introduce the first speaker and kick off the meeting.
Great, thanks, Christina. Yeah, so actually, there are a total of 4 speakers today. We have 2 from SETx and 2 from BSEC. And so we'll start with the SETx folks. So as you see, Elena is already starting to share her screen. The first speaker is going to be Elena McDonald-Buller. She's a senior research engineer at the Center for Energy and Environmental Resources at UT Austin. She's got more than 25 years of experience. Her research interests include air quality modeling, energy systems, analysis of air quality measurements, emissions inventory assessments, and development, and the influences of land use, land cover change, and extreme weather events on air quality. In addition to her own research activities, she has served as a project manager for the Texas Air Quality Research Program since 2012. Without further ado, Elena, why don't you take it away? And keep in mind that we have a total of 4 speakers. So with only 9 minutes in our program, you can do the math. We should probably try to keep your talk to 20 minutes or less.
Okay, thank you so much for everyone for being here today and for the opportunity to talk with you. I want to acknowledge my co-author, Dr. Yo Kimura, on this presentation. And so our air quality modeling work for Southeast Texas is centered around several core questions. First, how do concentrations of different air pollutants vary spatially and temporally across the region? How do local and regional emission sources contribute to air quality at specific locations within Southeast Texas? Do model predictions indicate hotspot locations considering the abundance and toxicity of different pollutants? And how do model predictions supplement and compare with ambient measurements in the region? We're also really excited about the opportunity for cross-theme interactions in this project. So models have a long history of being used for regulatory applications, being able to examine emission trend and control strategy scenarios. They also can support estimates of population exposure. And in this work, looking at compounding risks, so air quality, flooding, social vulnerability, for example, all leading into collaborative co-design strategies with the communities in Southeast Texas. So I'm identifying Southeast Texas as this region here in blue that lies along the Texas-Louisiana border. It includes 5 counties, Jefferson, Hardin, Orange, Newton, and Jasper, and that you can see depicted here. And we're using the comprehensive air quality model with extensions, or CAMEX. CAMEX has a long history in Texas for air quality research and regulatory applications. We began with a goal of leveraging a CAMEX modeling platform for April 1st through October 31st of 2019 that the Texas Commission on Environmental Quality, the TCEQ, has been using to support the state implementation plan for ozone. And we had been using it for quite a while to examine Mexico's energy sector planning and policies. We had several priorities for our CAMX platform. We had started with a large North American simulation with nested grids for the continental US and eastern and central Texas. And we wanted to extract a smaller, more computationally efficient domain, which we did, shown here in green, that has 4-kilometer resolution that spans the Neches River Basin, shown here in pink, to align with the hydrological modeling for the project. And we also added a 1-kilometer nest, this gray area here, to improve the spatial resolution where many communities are in close proximity to extensive industrial complexes like you see here. And the results that I'm going to share with you today are really focused in this 1-kilometer domain region. Historically, in Eastern Texas urban areas, attainment with the ozone standard has been a primary concern with the state, at least prior to the recent changes in the annual PM 2.5 standard. In this project, we have a particular focus on air toxics, and this required modification to our original model configuration to be able to explicitly represent all the air toxics that we wish. So I'm not going to talk about all the modifications that we made to the model, but I'm happy to talk a little bit more about how we're handling air toxics modeling offline or later on. So our initial simulations, the results I'm going to talk to you about today, I'm going to be showing results for benzene, styrene, 1,3-butadiene, acetonitrile, and ethylene oxide. So our CAMX modeling requires comprehensive emission inventory data across all source types, shown here, anthropogenic and biogenic. We've been using the most recent comprehensive national emissions inventory from EPA. It's the EPA 2020 NEI. That includes, it's a triennial emission inventory. It includes criteria pollutants, CAP precursors, and hazardous air pollutants or air toxics emissions from all source sectors in Texas and across other states throughout the US. And we also use information, it's supplemented with information from the Texas Commission, the TCEQ. So we've also found the EPA toxics release inventory. It doesn't, to be useful, it doesn't have the level of detail as the NEI, but it is an annual inventory for large industrial and federal facilities. And that is those are particularly important sources in this region of the United States, and in Texas as well. And so it is very useful for looking at trends and trend analysis, and also for quality assurance with the NEI. So the plot that I'm showing here on the right shows contributions from these source categories that I've shown above, these broad source categories that I've shown above, and from the 2020 NEI for each of the 5 pollutants that I mentioned. And both point sources and fires stand out for their contributions to emissions of these particular 5 air toxics in the region. So we're still addressing aspects of the model development, but I am going to share preliminary results that we have today. So these maps show 95th percentile concentrations over Jefferson County and a portion of Orange County. So it's this region right here. So the gray area that I showed earlier in the talk is shown here, the outline of that. That's our 1-kilometer domain. And then this black area is what I'm showing in the CAMX, the plots of the CAMX predictions right here for 4 of the pollutants that I mentioned: styrene, benzene, acetonitrile, and butadiene. And so this region of Southeast Texas is particularly rich in many of the industrial point sources. And so what I'm showing in these plots, we have our auto GC sites and our canister sampling sites depicted in either red by these red or green triangles. Emission sources, point source emissions of each of these 4 air toxics are shown relative to their magnitude with the circles, and then our CAMX model predictions of the 95th percentile concentration. So we're using percentile plots, for example, that I'm showing here, to examine some of our core questions, getting at similarities and differences in spatial patterns and relative hotspot locations and emission sources that are contributing to differences, which are evident between these four air toxics. I'm going to talk about ethylene oxide in a few minutes separately. So we're finding that grid cell maximum concentrations, which are shown here for benzene, that are not captured by the 95th percentile, are associated with fire activity in the region. And fires are episodic events. So this is actually an emission. This is a plot, temporal, just showing the temporal differences in emissions across the episode that we're modeling. And the orange spikes are fires. So fires are episodic events. We know that across the United States and here in Southeast Texas, and they contribute to air toxics concentrations in the region. Primarily, fire activity in Southeast Texas is associated with prescribed burning for restoration of native pine savanna ecosystems after years of wildfire suppression in the region. There are other sources of fire activity, include marsh burning, some agricultural burning, and then wildfires. So the plots that I'm going to show next show how different emission sources under different wind patterns contribute to the top 10% of predicted concentrations of benzene and styrene and acetonitrile at the locations of the AutoGC sites. So the plots that I was showing, the 95th percentile plots that I showed you a couple minutes ago, covered this region that I'm showing here in this map. And so I'm going to be showing results right now at the two AutoGC, some of the results at the two AutoGC sites, looking at how different emission sources in the region contribute under different wind patterns to concentrations at these two sites. And we're particularly looking at that higher end of the concentration distribution of these pollutants, so the top 10%. So here we have some broad source categories like on-road and non-road mobile sources, area sources, fires, but we've also broken out some of the point sources by industry, and we're tracking those emission source contributions individually. Okay, so what is this? What do these plots look like? So these are representing, so envision here, the wind directions depicted here show where the winds are coming from. And this is at that northern AutoGC sites. And this is showing the relative contributions of different source categories to benzene concentrations at that predicted benzene concentrations at that site by wind direction. And so we can see, so looking at the contribution to CAMX predicted concentrations at this site for benzene from 0 to 90 degrees. So when winds are coming from the north, northeast, and east, we can see contributions from regional sources within our 4-kilometer domain, as well as petrochemical manufacturing and petroleum refineries. And so these distributions change, as we move through the different wind directions at this site. Now, if we look at styrene moving to that southern AutoGC sites, this is the Nederland AutoGC site. The contributions here from northeast, easterly directions we see significant contribution from synthetic rubber manufacturing at that site, and rubber manufacturing is contributing within certain wind direction quadrants, and those contributions, for example, change if you're looking, for example, with winds from the south to the west, winds from the south or the west, and you see more contributions from petroleum refining operations. In contrast, most of the top 10% of CAMX predicted acetonitrile concentrations at that same AutoGC site are due to fires, and then also from, in some cases, synthetic rubber manufacturing, and then and solid waste disposal. So the basic overall, the point of the types of these plots is to look at how different industries can have distinct chemical signatures with variations in abundance and health and environmental effects. And there are both similarities and differences, even for facilities that fall within the same industrial classification. So for example, there are 4 synthetic rubber manufacturing facilities across the region, but only one is reporting emissions of acetonitrile. So styrene emissions between the different facilities can vary by as much as a factor of 50. So this isn't necessarily surprising because they can reflect, for example, differences in products or processes or other factors. But with the diversity of industries in the region, we want to use this information like this from the models and existing measurement networks and Pawel sniffer campaigns to be able to understand how emission sources are contributing to individual and mixtures of air toxics and differences in population exposure patterns across the region. So ethylene oxide, I'm going to talk about this just for a couple of minutes. It's an interesting case. EPA has characterized ethylene oxide as carcinogenic to humans by the inhalation route of exposure in 2016. And very recently, about a month ago, they promulgated more stringent emission standards and requirements for fence line monitoring. There has been to date, to the best of our knowledge, no ongoing monitoring of ethylene oxide in Southeast Texas. But there is a petrochemical manufacturer in Southeast Texas that had the largest reported air emissions in the US in the 2020 NEI and also in the 2022 TRI. And the emissions of ethylene oxide from this facility in 2022, the reported emissions were about 22% of the US total. And so, so we have been modeling this with both the emission inventory total from the 2020 NEI, as well as the higher total from 2022. So ethylene oxide is something that we are hoping to, that Pawel's been working hard to see if we can have measurements of that in the future. So really briefly, as I mentioned, cross-theme interactions are something also that we have been very excited about in this project. So we have also been starting to look at analyses for cross-theme decision-making. And as an example, some of our recent discussions centered around the selection of sites with both air and flooding concerns for collaborative co-design efforts with a community task force. So this began our thinking about the complexities of considering different factors in the region and how they could influence decisions about where specific efforts and resources could be allocated. Because, for example, the locations of schools, locations of different populations, and social vulnerability may or may not overlap. And so how do we consider all of these factors that we, when we want to think about where might be target spots for co-design efforts in the region, especially with the dense network of industrial facilities. So before I turn it over to Pawel, I'll just mention, so some of our ongoing work, we're continuing our quality assurance with our emissions processing and CAMEX modeling. We really look forward to working with Pawel in the future and looking at comparisons between model predictions and stationary measurements from existing networks, as well as his measurements, his stationary measurements and mobile measurements. So we'll continue our characterization of air toxics emission source contributions at specific locations and expanding our simulations and analyses to additional air toxics and continuing our cross-theme analyses. So with that, I'm going to turn it over to Pawel next.
Yeah, and as Pawel starts to pull his slides together for sharing, let me just give a brief introduction to him. And then I think at the end of Pawel's, we can have a little Q&A section for both Pawel and for Elena. So Pawel Misztal is an assistant professor also at UT Austin. He's in the Department of Civil Architecture and Environmental Engineering. He is a founder and director of the UT Sniffer Lab, which I'm sure you're going to hear a lot about. It focuses on big research questions in air quality and human health. He's an expert in novel time-resolved measurements of volatile organic compounds and has more than 10 years of experience measuring atmospheric chemical composition at different spatiotemporal scales, outdoors and indoors. Earlier, as a research specialist in the Department of Environmental Science, Policy, and Management at UC Berkeley, he led the first direct regional airborne VOC emission measurements in California to evaluate air quality models used by the California Air Resources Board. And with that, I'll turn it over to Pawel.
Thank you so much, David. And I'm very happy to be here and excited about focusing now a little bit more on observations. And want to mention that it's a big collaborative effort. We are collaborating with Elena on modeling and also with a lot of our groups. And we are very excited about inter-IFL collaborations. So David, could you please remind me when is my cutoff time? How many minutes do I have?
If you could get this in about 18 minutes from now, that'd be perfect.
Okay, excellent. Thank you so much. So I want to mention that we have like these amazing opportunities now to collaborate together. And I want to tell you a little bit more about the observational approaches and some preliminary results so far. I would like to acknowledge my passionate group members, also the group from Kerikini's group, and Lamar colleagues here. They are really amazing and very dedicated to this project. So I will be showing you some of the work that they have been doing. And I will start from the major question is, are we even detecting all the air toxics? Because sometimes you can hear in the news that, for example, regular air monitoring couldn't detect certain compounds, but the communities can smell it. So there is environmental justice direction that if they are alerted by the odor, then they're wondering if it's toxic or not. So I will tell about odors and toxicity a little bit more, and also focus on novel air quality measurements. But the classic measurements are also very useful, and you have heard from Elena, like TCQ has been continuously monitoring for a long period of time the criteria pollutants and HAPs and AutoGC. So we have a lot of those stations. It will be great to have even more of them, but we complement with some novel measurements. And in addition, the Lamar team, which is the local university in Beaumont, they also like build the capacity and do a lot of really nice fence line monitoring and GC measurements. So my group at UT Austin, we are very dedicated to addressing big research questions in air quality, outdoors and indoors, and factors affecting human health, because we don't fully yet understand all the factors that affect human health, and we know that air pollution is one of them. So we have this fully electric mobile van. It's a mobile lab that doesn't have a tailpipe. So it's really great for, I think it's the only mobile lab in the nation that is fully electric. And the nice thing about it is that you can sit in the plume, you can measure. It's also possible with other mobile labs, but we kind of enjoy this opportunity. So briefly about the instrument, it's a Focus Proton Transfer Reaction Time of Flight Mass Spectrometer. It's a long name, so we like to call it the sniffer. I will skip some method details for the sake of time, but I want to mention that this instrument is based on soft chemical ionization. It's a proton transfer reaction, and we are able to see the majority of volatile organic compounds. More than 1,000 compounds we can see at close to real time, less than 1 second. So I will move on to some air measurements, and we have a lot of different research questions, and some of them were covered by Elena already. I want to focus on some of the observational activities, such as spatiotemporal observations, evaluation of pollution hotspots, odor assessments, and we'll also show some really cool and recent measurements of indoor-outdoor measurements, how plume penetrate inside the houses. And we are currently working on quantified source apportionment. So I will focus on those activities. And these intensive field measurements, they included stationary measurements at Site A, which is very close to different industrial sources, such as elastomer, oil and gas. And here's, it's just next to this site. There's also a different site near Lamar University, also close to ExxonMobil, which is also a nice site, and we complemented with a lot of mobile measurements in different campaigns. This is how the mobile lab looks like. And the question is, what do you do with mobile measurements? So the idea is to accumulate a lot of statistically relevant data so that they can be integrated onto the census tracts for which we have health data, hospitalization rates, for example. And then we can also average over 1 kilometer grids, which helps comparisons and integrations with models. In addition, we need to do, we have done some exercise to compare with TCQ for the compounds that we overlap with. And we found a very good agreement overall with the average, but because the TCQ is hourly timescales, it oftentimes misses those incidental plumes that we can see very clearly. So let me ask a question. So what are the pollution hotspots in the Beaumont, Port Arthur area? So we were wondering about this question. And here I'm showing you actually how we were driving. It's a simple dashboard that we can look at the different segments and we can see what's going on. You can see the flag, the wind directions going from left to right. So the sniffer is blind to the freeway. What it sees are the compounds coming from the tire plant. And this is, for example, acetonitrile that you heard from Elena is pretty high in this region. It also is emitted here. There's isoprene as well. So we can look at these compounds. So if you plot it on a map, you can see that in different regions, there will be kind of different type of sources and compositional differences. So for example, the acetonitrile, which is in pink, which you just show it, it comes from a tire plant. If you go to a paper mill, now you can imagine what's happening with Amazon, so much paper is being produced. We went there and dimethyl sulfide is just through the roof there. There are also other compounds. It's a good marker there. And then styrene is emitted from the elastomer plant. It dominates. I will tell a little bit more about this plant the next slide. And benzene is a generic. It's oftentimes pretty high near oil and gas. So we can like really look into detail. We can look at these plumes. For example, this is the styrene plume. We're sitting in that plume, and we can take a look at the composition, which makes sense and is consistent with the industrial process. So the similar type of plumes we are observing when the wind is coming from those areas, and they detected at the community site. So I will focus a little bit on community exposure assessment here, the kind of first step to community exposure, because there are high schools, there is a high school, there are communities close to those areas. And as I mentioned before, communities are sometimes alerted by the bad odor. And so basically we were wondering, is there a quantified, because odor perception is not quantitative. You can quickly saturate on it, and some people are super smellers, some and so on. So we were wondering about more quantified approach to odor perception, parameter and chemical composition of odors. So EPA is also has, I'm showing here the EPA's odor wheel where, for example, communities can describe different types of odors. We have a community odor app that we are planning to integrate. But there's also a quantitative parameter which is called odor activity value. So if we basically take the concentration and divide it by olfactory threshold, then it basically corresponds to how odorous the air is. And it's more quantitative than just the, yeah. So if we sum up all the different compounds, like those hundreds of different compounds, we get total measured odor activity, and it can be combined with the field olfactometer that we have, or we can use literature values for different odor thresholds. So this is the result of that odor map. It's a total measured odor activity. And when I first saw it, when Evelyn Devro, who is working on a paper from this, when I first saw it, I was blown away, because I remember when we were going to those areas, it was exactly where the odor was the highest. But if we take a look at, for example, some of those odorous plumes, it's quite fascinating that sometimes only a few compounds actually contribute to the odor the most. And there are many odorless compounds. So this odor activity gives you the sense which compounds contribute. So for example, ethanethiol and dimethyl sulfide, they would have 2.8 odor activity. So it means like they contribute a lot. The smell like acetaldehyde, not so much, 1.2, but it's also very abundant, and cresol as and aromatics. So if we take a look at the abundance pie chart, it might look a little bit different than, for example, toxicity pie chart or odor pie chart. So this is like the most abundant in those styrene plumes near the high school, and where we observe about 51 ppb of total VOCs, and styrene was the most abundant VOC, followed by acetone. So now if we look at the toxicity pie chart, it's also styrene is dominating, but then the second one is phenol, not acetone, because acetone is relatively less toxic. And then we see acetaldehyde and some others. So it can be different. In some plumes can be quite different. And this case is actually a little bit similar. But then if you look at the odor pie chart, it basically sums up all those most odorous compounds. And I will now change gears a little bit and move into indoor air quality. So this is the Corsi code, basically illustrates how important the indoor air is, because we spend 79 years on average in indoor air, 69 years indoors, and then very little outdoors. So there are different processes indoors that and the outdoor air is penetrating. Like in steady state, it's always outdoors plus you get a lot of other sources emitted indoors. So generally, it needs to ventilate the house to reduce exposure to indoor sources. But then the question is, how do you ventilate if you have really high concentration outdoors? So it really makes a difference if you are in the plume versus when you are not in the plume and the air is cleaner outdoors. So yeah, the steady state model shows that it's outdoors plus the emission rate, and then basically can be diluted by ventilation flow rate. And so basically, what is exposure? So exposure is this area under the curve of concentration versus time. So this area under the curve is the exposure. So if we use a simple dynamic model for indoor air quality and for accumulation, and you can see how these areas under the curve change when you change air exchange rate. So for a well-ventilated house, it's really small compared to not well-ventilated houses. It's a huge effect of ventilation on reducing exposure. So we had this great opportunity to plug in, take the van that is electric and connect the tubes and switch between the living space and outdoor space. And this house was occupied by one female a person and one cat. His name is Fluffy, that contributed to the measurements. And now you can see like what is happening in red are the outdoor measurements, and in cyan are indoor measurements. So it's quite amazing that when you have the plume, actually the concentration outdoors is higher. It's not steady state, but if it's steady state, it's usually always higher indoors than outdoors. So here you can, I'm showing just two examples. One is styrene, and you can see lots of plumes. This is just outdoors. And this is dimethyl sulfide and ethanethiol. So you can see the pattern is different. So these represent two different sources, also some accumulation overnight and so on. So what is the concentration of those pollutants indoors for those period that we are measuring? And you can see styrenes actually generally on average is higher, except for the plumes, which will make it higher outdoors. And there's also and this is how it looks like for DMS. So if we plot all concentrations outdoors versus indoors for normal time when there are no pollution plumes, it's, as you can see, it's really is like outdoors plus for indoors. Like some compounds are orders of magnitude higher, like ethanol, acetone, and so on. So it's mostly outdoors is higher exposure. But we had an opportunity to measure indoors and outdoors when there were marsh fires, and we actually received the plume. Here's the plume that arrived at the site. It's enormous. And you can see, if you zoom in here, you can see how slowly it is penetrating because the house was closed up, was not ventilated well. And actually reducing ventilation helps for the plume, right? It's just important to remember that after the plume is over, it's actually good to increase the ventilation because immediately it's higher indoors than outdoors. So for this case, for the burning plume, we see lots of biomass burning markers that are well known, for example, furfural, furan, but also we see some cool other compounds such as thiazole, ethyl guaiacol, which is a smoke marker. In the styrene plume, the same thing, but fewer compounds, those that I showed you before when we were sitting in the styrene plume. So I basically arrived at the question, what can we do to reduce the exposure to communities? And I think one of the ways is to inform them, to basically educate the community. And basically, we deployed low-cost sensor networks in Beaumont. Also, we compared to Austin. So this is the SVOCs that we extracted from the filters in collaboration with Kerry's team. And air quality is not only chemical air quality, it's also microbial air quality. So we look at microbial composition. So this is like the homemade air quality sensors. And we tried affordable air cleaning solutions. You can see between those two lines how quickly the air comes in when we turn on the affordable filter. And here is also when we equip the filter with the pre-filters, carbon pre-filters, it also seems to be affected for VOCs. So I'm almost at the end of the talk, and I wanted to say that I'm extremely excited about these opportunities for joint IOPs. I hope to host many of you. And in particular, I know that BSEC has an ethylene oxide monitor. So if you guys would not mind coming over, we'll be very grateful actually to if you could complement some of those measurements. We are also planning to maybe purchase at some point that instrument. But also we are very happy to go to Baltimore, Chicago, Arizona, and basically strengthen or complement some other measurements as well. And in collaboration with with the supercomputer Texas Advanced Computing Center, trying to think about something that we could streamline together across all IFLs, that we could like build some databases. And so Will has been thinking a lot about it, and I will finish off with some conclusions. So we already did a lot of measurements, and we are integrating them with modeling. We characterize pollutions. We also thought about odor assessments. We're still refining some of these novel technologies, but it seems extremely promising. And yes, we are working with other teams, co-design, to try to inform communities and work together with communities. So the goal is to empower both the communities, the industries, and also expand our understanding. So we will also do some offline exposure analysis from those homes, and currently working on an IRB for those measurements. So with that, I would like to acknowledge a lot of collaborators, colleagues, and everyone. And yes, thank you for your attention.
All right, thank you, Pawel. So, and thank you, Elena. So we are not quite halfway through our time allotment. I do want to make sure that we give plenty of time for our BSEC speakers, but this might be a good opportunity to take a brief break here and ask any pressing questions that you might have for Elena or Pawel. And so you can just, there are a lot of people, so just raise your hand and we'll do it in the order of hand raising for the next 3 minutes or so. Anyone who does not get a chance to ask their questions, put it in the chat with the name of the person that it's addressed to, and we'll share that with the speaker later. So I see Matt Fraser's got his hand up. Start with Matt.
Thanks very much. Great to hear from the modeling from Elena and the measurements from Pawel. But my question is about the measurements. And we also have a Vocus 2R that we've been using for eddy covariance flux measurements, more for the biogenics rather than for, you know, kind of the unusual chemicals from chemical manufacturing in Southeast Texas. So we'd be very interested, like, kind of to see if you've ever tried to link up your PTRMS up to eddy covariance to try to get more quantitative flux measurements rather than just kind of identifying the source regions.
Thanks, Matthew, for this question. Yes, we tried actually eddy covariance measurements at the Yale Coastal Field Station, and that was part of this bigger Aroma project. And we also did like pilot measurements from Aerodyne's swamp. Like next to Aerodyne, there is the swamp. In the past, methane fluxes were used. So I think Vocus is extremely skillful in eddy covariance measurements. I'm very excited about the fact that you guys also have a Vocus and you are deploying it for the fluxes. We would be very happy to share our experience. I think the challenge is when you have 10 Hz data from the Vocus, it's enormous data. Initially, we couldn't crunch it, so we bought a gaming workstation with 128 gigabytes. And we were so happy because to crunch 1 month of eddy covariance data, it took us 2 months. But we were happy because we did that. And I was telling to Will from Texas Advanced Computing Center that it took us only 2 months. And he suggested, well, how about 1 minute? And so the current challenge would be to make it like single command and use some of the approaches. I think Toffware would need to think how to do it on a supercomputer, but also there are some other possibilities such as PTR with approach that could be converted to a single command on Linux.
So are there any other questions? I do see that Lloyd had a question in the chat for Elena. I don't know if you want to speak up now, but we have maybe 1 minute left for Q&A on this section before we move on.
Dave, thanks. Elena already answered it in the chat.
Perfect. Okay. I did not see that.
Did I answer your questions, Lloyd, about the emission? I think what you were getting at from the emissions, whether some of them could be coincident with the sea breeze from the Gulf?
Yes, that is what I was thinking about.
Okay, Okay, yeah, regarding like upstream oil and gas activity, there isn't much in the region. It's a good question. But it's very rich with petroleum refinery and petrochemical manufacturing. So yeah, along with other industries. Yeah.
Yeah, thank you. Yeah, I knew there was a lot of complexity, and I don't know the region, so that's why I was asking.
Yeah, no, it's great. It's a great question.
All right. Well, I think with that, we will go ahead and transition to our two speakers from BSEC. And I will introduce them one at a time and let them give their talk. So to start with, I think Peter DeCarlo is going to be the first up. So Peter DeCarlo is an associate professor in environmental health and engineering at Johns Hopkins. He studies atmospheric air pollution with applications to ambient air quality, including atmospheric aerosols and emissions from anthropogenic activities, including natural gas development. He has published extensively in the areas of atmospheric aerosols, particulate matter in particular, air quality and climate, and performed air quality measurements all over the world, and visited with many congressional offices to discuss climate change and air quality issues. With that, I'll let Peter share his screen, and you've got, like I said, try to keep it to 18 minutes or so, and that'll give us time for Q&A.
Great. Well, thank you all for the invitation to present. I'm going to focus my remarks on kind of an overview of BSEC's air quality theme and the work that we're doing. I think there's a lot of similarities to what's going on with Pawel and others, so I'm thankful that some of that introduction has already been done, and I'm looking forward to cross-IFL collaborations as well, so we can talk about that too. So just to kind of put everyone on the same page, this is a kind of a timeline for the various measurement components and some modeling components of the air quality theme for BSEC. So BSEC, as with the other IFLs, is kind of an initial 5-year investment. I've thrown Courage in here, which is the DOE ARM deployment that's starting this December and going for a year for the Baltimore project, as another kind of point to gauge. The Search Low Cost Sensor Network actually precedes BSEC, and you're going to hear about that from the next speaker, Kirsten Koehler. She'll talk about that deployment and results from that network. And that's a low-cost sensor network that covers Baltimore and gives us an idea of kind of how things have been changing over time. And we're looking forward to seeing that continue to keep up that data set going. I'm going to focus more talking about the air quality supersite measurements, and I'll get into what exactly that means, that are kind of just now starting up. We've got the equipment in place. We've started the measurements, and we'd like to see that extend beyond the kind of timeline of BSEC and figuring out how to do that going into the future. We also, similar to what Pawel just described, have some mobile measurement capabilities here at Hopkins. We were doing trace gas and aerosol composition measurements from a mobile lab. He is right. We do use gas. He uses batteries. I mean, it's fair. That was a fair thing to say for him to say. But we do have the aerosol components included in our mobile measurements, which I think are really important for understanding some of the regional characteristics of the Baltimore area. The AQ modeling activities really could extend beyond or in front of BSEC, but those are going on, and those are kind of the backdrop for things that we can compare to, similar to what you just saw for the Texas site. So I think we've got a lot going on, and there's a lot of different PIs, and I'm really thankful that I can kind of give this overview and highlight work from various PIs involved in this effort. So this is really the only slide I have on search, because Kirsten's going to give a much more detailed presentation about what search is and how it works. But this is basically the location throughout Baltimore of the search network. This was initially funded by an EPA grant, and Kirsten's been running this network now for, I think, over 5 years. 2018 or 2019 it began. Measurements of PM using low-cost sensors, ozone, nitrogen dioxide, carbon dioxide, methane, nitric oxide, and temperature and RH in the box for calibration purposes. And so what search allows us to do is see kind of spatial differences across the city of Baltimore. These are all within the Beltway. And additionally, you can look at kind of isolated events. If there's something like a fire at a coal terminal, for example, does that show up in the low-cost sensor network? And what are the differences in concentrations for various pollutants across the area when that does happen? And so we have this low-cost sensor network that gives kind of the spatial area and gives it in the context of 24/7 measurements, which is really nice to have because we only have one regulatory measurement of criteria pollutants in Baltimore City proper. So some key research tests, and I'm going to kind of intersperse kind of after each of these sections, what are some linkages or key research thrusts that we can kind of focus on as a way to kind of seed other IFLs to interact with or think how we're thinking about it within our IFL. And so the spatial variation of aerosols and trace gases is obviously one of the really nice benefits of having this low-cost sensor network throughout the city. Gives us these long-term averages that we can actually look year to year. It gives us acute events when there is a problem, and we can start to think about disparate exposures for communities within Baltimore, knowing that there's this classical, we describe as a black butterfly in terms of socioeconomic differences in population. We get seasonal variability in aerosols and trace gases, and we can link some of these measurements to higher resolution modeling that's also happening within this air quality theme. Additionally, what you can see here, we don't call it the sniffer lab, we call it mom and pop. This is our mobile lab here at Hopkins, mobile observatory measuring particles and other pollutants. That's our mom and pop acronym. So moving on, the air quality supersite location. Currently, we're making measurements only outdoors, but we're identifying a location, coordinating with the city of Baltimore and other developers to try to find a location where we can do consistent long-term indoor-outdoor measurements. And this is something that I've been working on now with Michael Waring at Drexel for going on over 10 years at this point. And the idea, similar to what Pawel was describing, is what happens outdoors does make its way to the indoor environment. And so we want to know outdoor air quality because we have all these correlations with health, but we also want to understand what gets into the indoor environment. In particular, particles drive a lot of the health impacts that we see. That's the association with most of the negative health impacts tend to be with particulate matter. And so understanding particulate matter and that transition of particulate matter as it goes into the indoor environment. I'll get into more details of that shortly. But what we plan to do is have kind of this automatic valve switching. We have an ACSM-X, which measures the chemical composition of particulate matter. We have a 2.5 micron lens on it, so it's measuring PM2.5 composition for sulfate, nitrate, organics as a class, but we can also run positive matrix factorization or source apportionment on that fraction to subdivide that organic component into different factors like traffic or cooking or secondary organic aerosol to understand what is in the outdoor and indoor population, what makes it indoors. We're getting size distributions with a scanning mobility particle sizer, and we have greenhouse gas and other trace gases that are being measured, potentially a PTRMS to be included, which we can use for my lab when it's not used for other projects. I'm going to give Ben Nault on my team some credit. He got the initial data set up for the air quality supersite. And so these are some of the initial figures that we see with the measurements that just started earlier this year. And what I'm showing you is a time series here of these organic chemical components of PM2.5. Color-coded, green is organic, blue is aerosol nitrate, red is aerosol sulfate, orange is the ammonium, which is the counter ion to nitrate and sulfate. And we really don't have much chloride. It's quite volatile, but we actually did see a few plumes here and there of some chloride. What you can see here and what I've subdivided on this other side over here, I think you can see my cursor, this is a high organic period where nitrate is quite low, and this is a high nitrate period. And what is happening in this kind of seasonal transition that we're having here in Baltimore, where it's getting cold and warm and cold and warm, is during these cold, more moist days, we have much higher nitrate. And then as it warms up, nitrate is semi-volatile. It doesn't go into the aerosol phase as much, and we have higher organic loadings, what we tend to see in this period. Excuse me. And so this is early data. I don't want to go into too much detail or dig too much into this data. We've really just got it in this last month. But it's really interesting to start to get this data and really understand what the implications are for processes, things like climate. Something that obviously is an interest for Department of Energy is aerosol life cycle and how these aerosols become CCN. And so understanding the seasonal changes in aerosol composition in this urban environment and what that means. As Powell pointed out, the implications for health and exposure are really important. Composition changes as you go from outdoors to indoors because you have temperature gradients, you have surfaces, you have potential of emissions in indoor spaces. And so what comes in from outside, how that composition of particulate matter changes are also important for understanding the health and exposure of populations to outdoor air pollutants. And this is important, especially when housing stock changes and how different housing stocks can be leakier or less leaky, and implications for what gets in, especially during things like wildfire events. And this is from data that we've taken in Philadelphia in a commercial building. It's not the same as residence, but just to illustrate how some of these seasonal gradients can impact the compositional change of particles as they come from the outdoors to the indoors. And so in wintertime, when you bring air from outside to the indoor environment, the relative humidity goes down because you warm it up, the temperature goes up, and that's pretty consistent. In the summer, sometimes the relative humidity goes up, sometimes it goes down, but generally if you have managed indoor temperatures, the temperature indoors is going to be lower than your outdoor temperature in a place like Baltimore and most of the mid-latitude and south of that areas in the US. And so if you take outdoor particles that have an average composition of something like 18% nitrate, 14% sulfate, et cetera, and you bring that into the indoor environment and heat it up in the wintertime, you lose some of that particulate matter mass because it's getting lost in that either filtration or it gets deposited as air goes through cracks in the building facade to come indoors. But you also lose some of the semi-volatile components. So you can see that nitrate, that blue color, shrinks when those particles come indoors. And that's a reflection of that increase in temperature and that loss of that semi-volatile material. In the summertime, we can also see a couple things. First of all, the composition of the particle initially changes. We don't have the nitrate that we see in the wintertime in the summertime. We have a lot more secondary organic aerosol due to the emissions from biomass and the subsequent chemistry that happens to form secondary organic aerosol. And so the overall composition of what's outdoor changes. And then when we bring that indoors and it's hot outside and cool inside, we get additional changes. And sometimes we get additional components coming into the aerosol based on the HVAC system and how the HVAC system handles the processing of air as it comes into indoor environments. And I don't want to dwell on it, I just want to kind of say that these temperature and relative humidity gradients are actually really important to consider when we're thinking about indoor aerosol of outdoor air, origin. And these are some papers that kind of go through what I'm showing you here, if people have interest in reading more about that. Another thing I wanted to point out when we're talking about seasonal differences is we think a lot about ozone chemistry driving secondary organic aerosol formation. And this transition of gas phase organics into the particulate matter is one of the largest mass components of aerosols in the summertime. In the wintertime, we can also see things like ozone generation during high sunlight hours and photochemistry happening. It's a lower degree of photochemistry, but we don't see this increase that we see in the summertime with organic aerosol. In the wintertime, we actually see a decrease, and this is probably boundary layer dilution. And so the sources of where this is coming from are likely biogenic, which kind of turn off in the mid-latitudes in the winter. And so we don't see that same trend with ozone. And so understanding and exploring those seasonal differences and what that means for particles and air coming into the indoor environment is also something we're quite interested in understanding once we get this indoor-outdoor long-term measurement site set up. And so I think there's a lot that we can do with the fixed measurement site. And so we're interested in the kind of current seasonal variability of aerosol and trace gas composition. One of the last kind of major campaigns looking at the Baltimore region, the Washington, D.C. region, was over 10 years ago. That was the Discover AQ campaign. And there's been a lot of changes since that time. Power generation has shifted from most of the coal-fired power plants have shut down, switching to natural gas, which changes the sulfate source. And so how that reflects in the composition of aerosols in this region are going to be important both for air quality and climate. As you take the sulfate out of the aerosol, are you adding nitrate to make up for that? Are you changing the hygroscopicity and therefore the CCN formation potential of these particles? And so these are things we're trying to think about in the broader fixed site context. We're also really interested in BSEC in climate extremes. And this is to think kind of into the future. What is a future climate going to look like? We do know that it's going to get hotter. And so on days where we're making measurements and we have kind of extreme heat, what are those what are those things that are driving the air quality issues on those heat days? And what does that mean when we think about future climate? How can we understand those processes and maybe try to minimize their impact in the future based on what we can measure and learn now? Obviously, there's an important modeling component. Making measurements gets a lot more powerful if you can help your models improve their skill in both predicting during normal situations as well as extreme events. And so what that means for future climate. If we can improve our models where we're getting the current extreme events pretty well, we can, I think, project into the future in a better way and better understand what the implications are going to be when we have more and more hot days in a changing climate. And then the modeling outdoor to indoor transport of aerosols and trace gases is really important. We want to connect with the health group, with a health theme within BSEC. We want to think about different housing types. Baltimore is a northeast city. There's a lot of row homes in the kind of center urban core. You get into more single family homes as you get farther out. So housing type changes, how people cool or heat their home. Do they have access to air conditioning? What that means in wildfire events. So if you have your windows open during a wildfire event, you're going to get a lot more exposure to wildfire pollution than if you have air conditioning and can keep your house buttoned up. What that means and how we can interact with the city, the state, and the federal level and think about these policy implications about cleaning. Powell did a great job explaining using something like a CR box is a relatively low-cost intervention that can reduce concentrations of particulate matter in the indoor environment. How can we incentivize that type of air cleaning in places where it's necessary and needed? And I just wanted to kind of highlight some of the work that has been done by one of the collaborators in the air quality theme, Michael Waring and his group, Brian Cummings, I think is on the call, where some of the measurements that we've done previously get used in a model which can then predict over much more of the heterogeneity of residential spaces or places and understand how indoor aerosol concentrations can be impacted by outdoor aerosol, thinking about phase change, thinking about the semi-volatile components and temperature gradients, and what that means for how we condition our air when we bring it into indoor environments. The mobile lab, mom and pop, similar to what Powell was talking about, we're really interested in this spatial characterization and using these research grade tools to understand both aerosol composition across a spatial area, as well as volatile organics and air toxics, using a combined PTRMS and GC instrument. A Vocus PTRMS linked up with a GC and measuring in parallel. The trace gases, methane, CO2 can link to the greenhouse gas group in BSEC, as well as just understanding potential sources by tagging those standard trace gases with other pollutants that we measure simultaneously to those and helping characterize plumes and where they might be coming from using those as linkage points. The mobile lab will have a role both in BSEC and in Courage. It's not completely linked to those. Our funding for the mobile lab actually comes from other sources, but we want to use it as much as possible to support these efforts as well and really understand the regional, I would say, soup that we have here in the Northeast, in the mid-Atlantic going into the Northeast from a pretty urbanized core along I-95 and understand the air that comes into Baltimore and exits Baltimore and what that means in the context of the fixed site. We're hoping to get some additional support for this using ASR funds with a proposal that's currently in review. Oh, I did not do my animation well here. I apologize. One of the things that we're really interested in is spatial gradients. And I just want to give a highlight with mobile measurements. This is a project that was done in Pennsylvania, and we didn't see a whole lot of difference in concentration across our measurement area for PM. When we looked at formaldehyde, however, we did actually see a pretty good spatial gradient, and I apologize for the pink box that's on top of it. That was supposed to be an animation, but we're seeing factors of 3 difference in formaldehyde across this. And so formaldehyde is an air toxic, and it's actually emitted by some of the industries in this region. And so we're using, in this case, 50 meter by 50 meter pixels to really understand how neighborhoods are disproportionately impacted by the formaldehyde in this space. The key takeaway here is on some of the smaller urban scales, the PM variation is not large, whereas differences in those VOC and HAP concentrations, I think Pawel did a great job of demonstrating this for Texas as well, are quite large and really can drive differences in exposure risk to populations and communities in these regions. The final piece of that is what we're trying to also do here is where we combine all of the HAPs that we're measuring. We look at non-cancer health endpoints systematically with a risk team here at Johns Hopkins to really understand what are the health impacts for exposure to pretty much everything at the same time for these. And so this is a paper that's currently in review in EHP, and we're hoping to get this out and share this kind of framework more broadly. I think it's applicable beyond just our study. And so what we can do with that is really look at the hazard for exposure for different systems. And so this final column here that I'm highlighting is if you sum up all the different exposures from all the different HAPs that we're measuring and sum them up, you get a cumulative impact for each of these non-cancer systemic health endpoints, so neurological health endpoints, respiratory, renal, ocular. And so we can do that and really get a good idea of what potential health risks we should look for in a community that we're making measurements with and in collaboration with. So I think, again, this is another important connection point with BSEC community partners. It's important to be able to connect these non-continuous mobile measurements with continuous low-cost sensors like the search network that Kirsten's about to talk about. We can map regional and environmental upwind and downwind of Baltimore, both particles and trace gases. We're really looking forward to using this in the Courage intensive observational period and connecting some of the ARM sites in that framework. And coordinate with the greenhouse gas team, link up with the health team, and I think, as mentioned by Pawel, coordinate across IFLs, thinking about VOC HAP measurements and implications for exposure. And yes, we do have an ethylene oxide monitor, and we're excited to share that. We just made some measurements last year in Louisiana and have some results coming out next month on that. So I'm going to leave this up. This is kind of the final conclusion slide, just bringing you back to kind of where we started. This is the BSEC timeline. The search, which you'll hear about next, kind of precedes and hopefully goes beyond what we have for BSEC, and then the various measurements and activities going on. So I'm looking forward to working with other IFLs and within the BSEC team to really get a better characterization of what's going on in air quality in this region. So with that, I will stop my share and turn the mic over to Kirsten.
Okay, thanks, Peter. So let me go ahead and just briefly introduce Kirsten while she pulls up her slides. So Kirsten Koehler is a professor also in environmental health and engineering at Hopkins. Her research seeks to improve exposure assessment methods to inform occupational and public health policy. She uses direct reading or real-time monitors to improve spatiotemporal exposure assessment and to couple estimated exposures with location data to identify occupational sources of hazards. With that, Kirsten, please take it away. If you keep it to 18 to 19 minutes or so. And you are muted if you're talking.
Sorry about that. I was asking whether everybody's seeing the correct full screen mode. Okay, I'm going to assume silence is yes. Okay. Thanks for the introduction, Pete. And I'm going to expand a little bit more on some of our lower cost approaches for ambient and indoor air quality assessments. This is built upon work that was originally funded through an Air and Climate Center funded by the EPA. It was a partnership with Johns Hopkins and Yale and some other universities. And then fortunately through BSEC, we've been able to continue this network. And Pete and I are in the same department, but my primary appointment is in the School of Public Health. So I'm typically thinking about exposure assessment to indoor and outdoor contaminants using a few different approaches. We have done studies looking at personal and occupational exposures, actually having people carry equipment. Often we're doing this in a kind of integrated way. The lower cost sensors are giving us better ability to capture some temporal variability. Sometimes we're relying on state-run, air pollution monitoring networks, but more and more so trying to get, more dense, ability to capture spatial and temporal variability through something like low-cost sensor networks. And so these have advantages of being able to capture quite a few hazards with available sensors, provide higher space and time resolution over people. And we also created a portable version of this that people could carry around as they went about their activities. So this is what our monitor looks like. The stationary one is shown in the upper left there. We always say it's about the size of a toaster. It contains sensors for the plant tower for particulate matter, ozone, NO, NO2, CO, CO2, methane, and then temperature and relative humidity. The temperature and relative humidity are measured inside the box, so are not really ambient temperature measurements, but really what are needed to calibrate the sensors. And then in the lower right there, you can see our portable version of this that has, some electronics that could be put in a backpack or something, where all of the sensors can be worn kind of shoulder mounted in the breathing zone to be able to characterize personal exposures as people go through different microenvironments. So for the sensor network that we're thinking about using most for the BSEC project, this, as Pete mentioned, has been ongoing since 2018. The first few sensors kind of in more full force since 2019. We first decided where to put them based on a weighted random sampling approach, where we developed weights based on air pollution, measurements of NO2 from satellite derived estimates, proximity to energy generating units, electricity generating units, transportation, point sources, and population density, and then combine those into a total weight that we use for our weighted random sampling approach. And then because our monitors do require power, then found locations that we could actually put these near these sampling locations that are identified both to be near larger sources, but also to show gradients across roughly the city, kind of within the 695 Beltway highway that surrounds the city. So this is a map of our current network. We have about 45 measurement sites. And we also are fortunate to be able to collaborate with NIST and MDE, the Maryland Department of the Environment, to be able to have some co-location of our low-cost sensors with their high-quality measurements, both air pollutants and greenhouse gases. And so this gives us detailed reliability data on our low-cost sensor network. We've also been talking with MDE about, of course, you can see the bridge that no longer exists down here in Baltimore, and thinking about how we can use this data to help understand not only what happened on the day, but also massive changes in traffic patterns that are occurring as trucks and other vehicles are being rerouted around the city. This data all comes in live through a cellular connection network. We store this data all online, and then everything also has redundant SD card backup in case of communications failures, so we can be looking at data in near real time. We've expended a lot of our effort to this point on various calibration approaches. For today, I'm going to focus on our PM measurements, but happy to talk about other sensors if people are interested in theirs time. We've developed approaches to account for cross sensitivities, particularly for the gas phase sensors, accounting for sensor drift, and thinking about optimal co-location periods of keeping low-cost sensors with higher cross measurements to develop accurate and reliable calibrations. So this is some of the data that we started with the PM 2.5 sensors. You can see the MDE measurements in the red line there. PM 2.5 sensors generally greatly overestimate mass concentrations as their raw data. This is well known. If you calibrate just for temperature and relative humidity, you can do better. And then we have developed additional calibrations using also indicators for weekday versus weekend and daytime versus nighttime, and additional residual temperature and relative humidity bias to do much better. We've also been using probabilistic approaches, using gradient boosted decision trees, using the NG-Boost package. This has also allowed us to do just as well with no lab calibration as we were doing with, field calibration on top of a lab calibration from the linear regression, showing root mean squared errors of about 3 for hourly measurements. And this type of approach also in the map, you can see, allows us to look probabilistically at whether certain neighborhoods are exceeding some threshold of interest. So this is for a daily average, showing highest concentrations on this specific day, kind of following this big highway that goes through the center of the city. But that's not a universally true. We see lots of different patterns across the city on different days, with generally there being higher spatial variability within a day, but as you kind of average to months or seasons or years, a lot of that spatial variability starts to average out. We've also, we're using a plan tower sensor. It's not the exact same model as the one that's in something like the Purple Air device, but they're very similar. And so we've also been thinking about, our approaches and how we could facilitate better comparison across lots of different types of study sites. For example, using Carolyn Bark-John's United States-wide correction factor that has been developed for the Purple Air sensor. And in fact, we see that there are some small differences whether we use the different calibration approaches that we have developed versus the EPA approach. But that for the sake of harmonization and perhaps across different, centers, as well as being able to include broader low-cost sensor networks within our measurement campaigns. This is one approach, and a biostatistician who's been working with us, Abi Dada, and his students have also been developing calibration approaches that explicitly account for differences between different types of networks, bringing those together along with reference measurements to develop maps of spatial and temporal variability. And well, we've started with PM, but could be done with lots of different sensor types. We've also been looking at using the Purple Air in-home assessments. I'm going to talk a little bit more about our in-home measurements in a moment, but this is showing weekly in-home average PM 2.5 concentrations measured in Baltimore City. Yes, those are going up to 300 micrograms per cubic meter. In some of these homes, the concentrations are quite high when smoking is present in particular. So the Purple Air concentration is on the y-axis, and gravimetric weekly average PM 2.5 mass concentrations on the x-axis. Initially, the raw sensor in the green, greatly overestimating the true concentrations in the 1-to-1 line shown in the solid black line. But whether we use our Baltimore-specific calibration or the EPA's US-wide calibration, we can get to where we're doing quite a good job at estimating mass concentrations, particularly up to about 50 or so micrograms per cubic meter, a little bit more uncertainty as concentrations get above that, but I think also enough to know that we can distinguish and there's very high correlation between these different measurements. So allowing us to understand kind of rank order of where people fall on kind of an exposure continuum. So how can we put all this together? This is just narrowed down to Baltimore City here for 4th of July, a day we know is always interesting. In the morning, 5 to 10 micrograms per cubic meter of our kind of normal conditions. And then as the afternoon builds in, you can see higher concentrations building across the city. And later, as sun goes down, really these intense hotspots of concentrations, probably due to fireworks, not only in the center of the city where the city was hosting fireworks, but also in specific neighborhoods that were probably contributing with their own fireworks as well. So So that's just an example of kind of what we can get from the sensor network. With the last few minutes, I just wanted to measure in briefly that I'm working also with the health theme, and Meredith McCormick and others, where we've been doing studies for a long time looking at indoor air quality, measuring PM2.5, PM10, NO2, airborne nicotine, allergen, measured and settled and surface dust, as well as temperature and relative humidity measurements in homes really over the last 20 years from before I started at Hopkins, being able to show that indoor concentrations greatly exceed outdoor concentrations. You can see this is data from 2001 to 2003, but and the annual EPA annual limit much higher than its current level. But you know, these trends still hold today, in that we have fewer households that are above 50 micrograms per cubic meter than we maybe did 20 years ago, but we still see some. And then this also gives us the opportunity to think about within these studies where we have detailed characterization of different household types, household activities, presence of gas stoves, different things, how PM2.5, NO2, other important indoor air pollutants can impact exposures for these families. And this is really important because we've seen really large variability. This is for a study that we did looking at 50 children who had asthma. There was measurement equipment set up inside their home doing weekly average measurements, as well as asking the children to carry a backpack, doing personal exposure assessment for 4 days during that week. And then of course we can get data from the central monitor that might be used for a typical exposure assessment, and that's shown in the yellow. So for some kids, you can kind of see the difference between their outdoor ambient concentration in the yellow, a little bit lower than their home concentrations and their personal measurements, but not a huge amount of variability. Whereas for other children, their indoor mass concentrations to PM2.5 greatly exceeding the ambient concentrations, and personal exposures on some days could be even higher than that. So because of these findings over the years, we're also looking at interventions to improve indoor air quality. And so we've been thinking about using engineering approaches like air purifiers, air cleaners, HEPA air cleaners, and those with activated carbon to be able to improve air quality in homes. We've done this in studies both of older adults with chronic obstructive pulmonary disease, as well as among children and their families, children who have asthma. And so we have seen that the use of these purifiers across a large number of households can result in the one study, a 28% reduction in NO2, a 50 to 60% reduction in PM2.5, depending on the study. And so we think these are really meaningful and actually have been shown, particularly among the adults with COPD, to have measurable health benefits, where those with COPD had fewer symptoms, less need for rescue medication use, and that the effect was strongest for people who used the purifier at least 80% of the time. So we think this is strong evidence and really provides us with, a long time scale of measurements characterizing the indoor air quality, characterizing heat exposures. A lot of these homes can be quite warm, as a function of the type of neighborhood people are in, the type of housing they have, presence of gas appliances, et cetera, that we think are really important for helping us better characterize kind of exposures across the city. And so I'll just wrap up by thanking a lot of different people who have contributed to the sensor network over the years, as well as lots of people within the Breathe Center, who I haven't mentioned as explicitly, but I'll stop there. Thanks.
All right. Thank you, Kirsten. So, and thank you, Peter, as well. So if there are any questions for Peter or Kirsten, we have about 6 minutes left. We want to take the last minute or two for admin discussion, but any questions, just feel free to raise your hand. Everything was so clear, there's no questions. I guess in that case, I can hand it back over to Christina and she can close us out.
Yes, thank you, Dave. And thank you for all the speakers. It was really very interesting presentations. I see a lot of potential connecting points across the IFLs. I can see a lot of potential for really sharing your knowledge across and really to the benefit of the urban science within BER. I wanted to conclude this just inviting you to the next in the series of these seminars. Is going to be in August. It's going to focus on urban heat. We have a number of presenters that have volunteered to share their work. However, we don't have a final list of talks, and so we're gonna look out for. You're gonna send you a message to look out for an announcement of the new speakers for the August session and urban heat. I hope you enjoyed the series so far. If you have suggestions on new topics that would be interesting to be discussed for all the 4 IFLs, please let us know. And thank you so much for participating, and I'll see you all in August.
Thank you.
Thank you.